Welcome to the PrSAT 3.0 demo video. On the left here, I've got my browser open. This is the main PrSAT page. And here you get information about the basic syntax of PrSAT, which is just ASCII, pretty standard notation for logical formulas, and then probability statements and probability terms, and arithmetic operators and comparisons. That's the language we're using. Anyhow, let's go ahead and launch the app itself. That'll launch in a new tab. And here we've got a link to the official page. This is a link to the current video, and then here is a link to this text file over here. So these are the examples, some examples I'm going to go through as we go through, so you can download the text file here. But before we do that, let's just load in some constraints just by typing in. And so you'll notice that when you're typing in, as you type, if what you have is not a well-formed statement about probability calculus that has, that can be evaluated as having a truth value, then you'll get this syntax error here. But eventually, if you complete a statement that is parsable as a probability statement, then it'll be rendered here in more cleaner mathematical notation. Anyhow, once you decide you want to search for a model satisfying these constraints, you just click Find Model. And you'll notice now a whole new thing opens up. You get this model that was found. This one has a 0 in it, so it's not a regular model. We could find a regular model if we want by clicking the regular option. Oh, actually, in this case, there are no regular models because, yeah, that has probability 1, which means there are zeros. But if this was, say, 9/10, then we could find a model that was regular. But let's go back to this one, which will necessarily have a 0 in it. Okay, it'll necessarily have this 0. And you'll notice also down here are the translated constraints. So what's happening with the solver is it's translating these statements into algebra using the technique that can be found in the reference here, this paper that I wrote some years ago, called A Decision Procedure for Probability Calculus with Applications. That explains how to translate statements in probability calculus into algebraic statements. And the only thing we really assume here is that these numbers are between 0 and 1 and add up to 1. So these probabilities that are assigned to the states, those have to be between 0 and 1 and add up to 1. Those are the only things we're assuming. And then we have like the ratio definition of conditional probability, of course, and then just adding up numbers to get unconditional probabilities in the way described in that paper. Anywho, so that gives you the translated constraints. You'll also notice there's some other options here. You can save the table as an image, so that'll just save the table out to a PNG file, which is nice if you want to just have the model that I found for a given problem. You can save the translated constraints, and those are like quasi-LaTeX format, right? So this is almost LaTeX, except I'm not including math mode or anything like that. We're not including that here. Okay. Good. So now let's see. What else have we got? Well, we've got, there's a timeout thing here. You can change this. Most problems will run, if they'll solve in less than a minute. So this is a good default. We'll look at some problems that take 30, 40 seconds later. Anyhow, and now you've also got this where you can evaluate expressions on the model. So if you want to know the value of a given probability, you just type in that term, and it'll calculate that probability. And you got to be careful, of course, here because in this case, y and not x, this statement here, has probability 0, which we can just confirm, but of course that's given by the table itself. That's one of the states. And here you'll notice, this conditional probability, which normally would be 0, is not defined because this thing has probability 0. And so that's going to happen. You can get zeros here, but then you have to be careful because some of the conditional probabilities will be undefined, and it will catch that, and it'll tell you that you're dividing by 0. Okay, what else? Yeah, okay, so you can clear these by doing that, and if you just reload the page, you can clear and get a totally clean slate, and it'll reload Z3 and all that stuff, so it'll be in a fresh state. Let's bring in some problems from here. So here's a simple claim which can't be true. It says the probability of the material conditional is less than the probability of its consequent given its antecedent, but of course that can't happen, so unsatisfiable. So here it'll just show you the translated constraints, tell you that it's unsatisfiable, give you a blank table that just shows you the key for the translation. And you can, of course, output the constraints, but you can't output a model. There is no model, okay, because this is unsatisfiable. Now, of course, there's many models where the thing is true, and of course, it's true on every model, so it's a theorem. Okay, so that's one problem. Here's another thing that's different. Here's an interesting form of Bayes' theorem that I kind of like. So it's a kind of a weird form of Bayes' theorem, but that is an instance, that is a way of writing Bayes' theorem. And of course, I'm denying that it's true, so we can verify that it must be true just by looking for a model and seeing that it's unsatisfiable. And if you look at the algebraic translation, you can see it's obvious why it's a little more obvious why it's unsatisfiable. Okay. Now, let's look at some cases of interesting non-theorems or cases where there are models. And here I'm going to take advantage of the batch input. So batch input, you just have constraints separated by new lines, and then you parse them. They all get parsed immediately, and then you find a model. And so this is, of course, a Simpson's paradox reversal. It's a case where x and y are positively correlated given z, and they're positively correlated given not z, but unconditionally they're negatively correlated. So this is a Simpson reversal. And this is one that's not regular, but of course there are plenty of regular examples. This is kind of a complicated model with a lot of with a big denominator, but of course you can simplify this by adding some marginal constraints. So if we just say let's do it so the probability of x is a half, okay, now it gets much simpler. And maybe we can make it even simpler by making and maybe can we get it even with a smaller denominator? I don't know. Let's see. No, that makes it worse. So that's a nice simple model, a nice simple Simpson reversal with relatively small fractions there. Okay, that's a good one. Here's a fun one. So let's paste this in, parse these. And there's a unique model satisfying these constraints. You have 3 constraints, but since you only have 2 atomic sentences, you have only 3 variables, basically 3 unknowns. So this determines a unique distribution. And it happens to be one with irrational numbers in it. And that's because when you solve these equations, you end up solving a quadratic, which happens to have some irrational solutions here when you restrict it to the simplex. And of course, if you calculate, say, the probability of B, that's going to be an irrational value on the model. Okay, now let's look at some more interesting theorems. We've seen some simple theorems verified with this, but let's verify a more complicated theorem. So this is Reichenbach's conjunctive fork theorem. It says if C is a common cause of E1 and E2, that means if C raises the probability of E1 and it also raises the probability of E2, and it screens off E1 from E2, then E1 and E2 have to be unconditionally correlated. So if you then deny that they're correlated, this is going to be unsatisfiable. And that pretty much instantly verifies this theorem. Not a trivial thing to verify. Of course, if you want to find examples of conjunctive forks, that's pretty easy. There'll be all kinds of examples of conjunctive forks, and you can get ones with whatever probabilities you want, and so on. So you can do that. So that's a nice one, Reichenbach's theorem. Here's another theorem that's kind of cool in a related vein, and that is that screening off is sufficient for the transitivity of positive correlation. So if A and B are correlated and B and C are correlated, it doesn't necessarily follow that A and C are correlated. So if these are all the constraints you have, then in fact there'll be many counterexamples to that, because positive correlation is not transitive in general. But if you add in these screening off constraints, you say that A screens off B from C. Well, now that's a theorem. So that means screening off is sufficient for transitivity of positive relevance. Okay, now let's do some interesting non-theorems here. So this is a classic problem that you'll see in every textbook. Just because X and Y are independent and X and Z are independent and Y and Z are independent, so they're all pairwise independent, doesn't mean they're independent simplicative, doesn't mean that they're three-wise independent. And in this case, when you ask the solver just to do this problem outright, it actually finds irrational values, which is fine, but of course you can simplify this just by adding a numerical constraint. And you get a nice simple model, a simple case where two-wise dependence doesn't entail three-wise independence. Okay, now here's something harder, considerably harder. What about when you have four events that are pairwise and three-wise independent, but not four-wise independent? Well, okay, it won't solve this one, and you can let it run for as long as you want. It's not going to solve it. This is a very complicated algebraic thing to do, so it won't solve it. But if you add a marginal constraint, like probability of X is a half, then it will find, it should find a model. Let's see, maybe we have to ask it to find a regular model. Let's see if it finds a model. Might take some time. Yep, but it does. But okay, again, it's got irrational numbers in it. But we can fix that just by adding another marginal constraint. And now you get a nice, very simple model where you have two-wise independence, three-wise independence, but not four-wise independence. Okay, that's a fun one. Okay, here's one that's interesting because it's one that has irregular models. So there's some irregular models that satisfy these constraints. Okay, but there's no regular models. And that's somewhat interesting because nothing here is explicitly assigning probability 1 or 0 to anything in any obvious way. It's just that the combination of constraints forces there to be some zeros, and in particular, it's going to force these two states to have zero probability. All right. Now let's look at something a theorem that's a bit more complicated. So parse these. So here's a theorem from a paper that I wrote with Jim Hawthorne called The Waste and Tasks and the Paradox of Confirmation. So this is a problem from confirmation theory, basically involving the Raven's paradox or the waste and task. It would be applicable to both of those, the way they're set up in the paper. And this is hard. This is not a trivial, this is theorem 4 from our paper, and that was not an easy thing for us to prove. And it's not an easy thing for the solver to solve. I think it solves in around 35 seconds. Let's see. So it should solve in the next few seconds if I'm right about this. Maybe 40 seconds. Well, if we're lucky, maybe it's 40 seconds that it was. Yeah, it's about 40 seconds it solves. So that verifies the theorem, but it's okay. That's a hard one. As I said, most of the problems that I've looked at, if they solve in less than a minute. And now you can, if you want to find a model in which all the conditions of the theorem are satisfied, which of course there are many such models, then there won't be any regular models here though, because one of the constraints is extremal. So if you hit regular, then of course there won't be any. This one again will run for about 40 seconds, and then it will find a model satisfying all the conditions of the theorem. And then, of course, obviously, therefore, the conclusion of the theorem. So this should finish in a few seconds. So this one's pretty complicated. Now, in this case, since we're finding a model, what we could do is see if adding constraints makes it easier. It often does. So maybe we'll do that. So here, there you go. There's a nice model. But what if I say, can we do it this way? Now that constraint might not be compatible with these constraints in this case. So yeah, I'm not even sure if it is. So who knows? This one's hard. But you can cancel the search, and that's fine. You'll still have all your constraints here translated that were in from the previous problem, and then you can just clear things out. Okay, let me close with an industrial strength problem. This one involves 6 variables and lots of constraints. And we're going to look for a regular model here. There will be one. This corresponds to a Bayesian network structure of a certain kind. Anyway, there's 6 variables, and if you look at these algebraic constraints, they're pretty ungodly. Yeah, so no one's finding this model by hand, obviously. Anyway, it's nice that we can find this model, and then of course you can calculate whatever probabilities you want on this model. And you can even output this as a table, as a picture. It's pretty big, okay, but zoom in. It's pretty high res PNG, so it works pretty well, even for big tables. Okay, well, I think that's all I wanted to show, so I'll stop there.